So hello everyone, and I see that everybody here is from Northwestern. So thank you for joining for our first session of the spring program for the Virtual Inter-University Symposium on Infrastructure Management. So today we have Max and Meredith Raymer presenting their work. So each presentation should be about 20 minutes long, after which we'll take questions from the audience. So just speak up your questions or use the chat feature. And so just want to point out that this meeting is being recorded, and we'll be posting the recording publicly shortly after. So thank you for attending. And with that, I'd like to introduce our first speaker. So Max is a PhD candidate in transportation engineering at Northwestern University. Max obtained his bachelor's degree in civil engineering at the University of Hong Kong, and his research focuses are on smart mobility, network analysis, and data analytics with projects in rail decarbonization and freight resilience that we'll be hearing about today. Before joining Northwestern, he worked at MTR, a Hong Kong railway company, and is a chartered civil engineer in the UK and Hong Kong. So with that, I'll hand it over to Max. Please go ahead and share your screen.
Yeah, thank you, Adrian. Let me share our slide today. Yep. Can everyone see that?
Yep.
Great. So thank you very much, and really happy to see everyone here today. Today we will talk about a research project that has been going on for more than a year here at Northwestern with Adrian Hernandez, Professor Pablo Durango-Cohen, and Professor Hani Mamasani. So the topic here is the trading of energy storage and payload, and an analytical model for freight train configuration. So I will briefly introduce the background, that is the freight rail decarbonization, as well as the energy storage tender car to support the range. Then we will formulate the problem with an EOQ model, that is economic order quantity. Then I will go through some numerical examples to demonstrate the model, as well as network-wide freight market analysis. In the end, we'll reach some conclusions and insights for the rail industry. So I'm sure most of you will be very familiar with the rail industry in America. Freight rail is branded as the backbone of the American economy, and is supported around 40% of the US freight. But it also among the greenest mode of transportation, because it only accounts for around 2% of transportation-related greenhouse gas emissions, according to the Association of American Railroads. But to address the climate change, the railroads industry is trying to make themselves even greener with more R&D of new energy sources, such as battery electric trains or hydrogen locomotives. However, there is a critical constraint on the limitations in battery capacity as well as the range. So if you are interested in more about rail decarbonization, we would like to invite you to click to our new friend dashboard later. That these tools for you to select different railroads, different energy scenarios, and different rail commodities, and you can see which kind of strategy would be the best to decarbonize our rail freight network. And we have also produced some new friend insights. There is some publications for the industries to consider different perspectives of the problems. So going back to the energy storage tender car, to address the issues of range that I just mentioned, that is to say, if the battery capacity is not big enough, then the train will have to stop multiple times in order to recharge. And this is annoying to drivers, and particularly annoying to railroads, because any delay cost would mean extra time incurred to using the trains, as well as delay to deliver the freight shipment. So there's a proposal of using multiple tender cars for the locomotives. And for tender car, actually that means rail cars with energy storage media on it, such as battery, so as to power the connected locomotives to provide an extended range. And we have seen some papers recently, such as the Popovich et al. 2021 from Berkeley Lawrence National Lab. They assume a 14 megawatt-hour battery configuration with a range of 240 kilometers. And they have shown reductions in greenhouse gas emissions, as well as financial competitiveness of these settings. And a similar test case in Australia showing that different freight origin destination pairs in Australia require different battery capacity. And like 14 megawatts hour, which is actually very ambitious estimate in the current technology, can only satisfy some of the markets. And if we have to go for like a longer line haul pairs, then we will need a bigger battery and as much as 30 megawatt hours, which is only achievable if we include like hydrogen fuel cell here or multiple batteries. And therefore, we look into the problem. There's the trade-off between the rail cars and the battery tender cars. To be more specific, we introduced a term alpha here. There's the ratio of the weight of an energy storage tender car to the weight of an FH loaded rail car. For example, if one energy storage tender car is as heavy as 2 revenue cars, then alpha would be 2. And if we want to add 1 battery tender car to the train, then we will have to take away 2 revenue rail cars. Or to say, if we want to put in 2 battery tenders, then we'll have to take away 4. So you can see, if we want to increase the number of battery tender cars, then we'll have to reduce the number of revenue rail cars that is the freight shipment to be carried by the train. And if we want to ship the same amount of freight shipment with more batteries, then we will have to put in more trains. That means more crews, more locomotives, and higher cost. So this is the trade-off issue that we're looking here. If we add in more energy storage tender cars per train, that would mean longer range because of the higher battery capacity in total. So we can reduce the number of charging stops and therefore reduce the delay, or we call them inventory carrying costs. However, that also means we are carrying fewer revenue cars per train. So the total payload per train is lower, and we require more trains to ship the same amount of goods. And that would mean higher fixed costs. And this is the trade-off that we have to look at. To optimize the number of energy storage tender cars in these circumstances, we have formulated the problem with an economic order quantity model, an EOQ model, which is a classic problem. That means the order quantity actually determines the order frequency and the inventory held, and therefore the associated ordering, inventory carrying, and purchasing costs. So now let's look into the actual formulation of our problem. We formulated the total cost as 3 components. The first one is the fixed cost. For fixed cost, on the right-hand side, you can see Q over L minus alpha N, where L minus alpha N is the number of revenue rail cars, and Q is the total demand. So the term here actually refers to the number of trains required to ship the total shipment. And the K is the constant fixed cost. And in equation 3 here, you can see the K can be expressed as a function of N, the number of battery tender cars. And there are also 3 components for that. The first one is locomotive cost. That's how much to operate a locomotive to ship the goods. The second term is energy storage cost. How much is a battery tender car, for example. And the last term is the energy cost to charge the battery. And we are now presenting a simplified term of K, which is a constant. And it does not vary with the number of energy storage tender cars N here. But in our paper, we have also shown the generalization for fixed cost, K as a function of N. We'll also show similar results that we will discuss. So for the second term of the total cost, that is the holding cost, or you can think of it as the delay cost. It's actually just the product of a constant H with the total trip duration and the demand. For the total trip duration in equation 2, that's actually just the original trip duration without any delay, plus the stopping time per stops and the number of stops. And the number of stops is, of course, the trip distance divided by the range of the battery. And the last term of the total cost is purchasing cost. That is the cost to ship a unit of shipment. And because it does not vary with the number of tender cars, etc., so there's not of interest here. And to put it into perspective, we can actually look into this graph. This is showing the cost in the y-axis, and the x-axis is the number of energy storage tender cars. So for the red solid line, that is the total cost, which you can see here is a convex function. And we also show it with the derivatives that the total cost is actually convex with respect to the number of energy storage tender cars. And then for the holding cost, which is the orange dotted line here, is monotonically decreasing. So that means if we add in more energy storage tender cars, then we can actually reduce the charging time, and therefore reduce the number of stops. So therefore, the delay cost will increase when we have more battery cars. And in contrast, the fixed cost, which is a green dashed line here, is monotonically increasing. And that means when we increase the number of energy storage tender cars, we are taking away the revenue car, rail car. And therefore, we need more trains to ship the same amount of goods. And therefore, the fixed cost increases. And with our EOQ formulation, because it's analytical, therefore we can have the analytical formula of the optimal values. For example, we derived the optimal number of energy storage tender cars here as a function of L, that is the length of train, over alpha plus square root of terms of costs, charging times, as well as the range and distance. And the same goes to the optimal range and minimum total cost. So to demonstrate the model and the results in a simpler way, we now look into 3 numerical examples in the American freight rail network. The first one is from Los Angeles to Chicago, and the second one is from Powder River Basin in Wyoming to Chicago. So the first one from LA to Chicago, we look into the intermodal freight and automotive freight. So the key difference between the two different commodities is that intermodal freight is usually more time sensitive. Because imagine if you buy a TV online, which is manufactured in Asia, and they have to ship from Asia to California, West Coast, then they will be transloaded to train to Chicago. And if you get on Amazon, usually you want it to deliver on the next day. So the time value is very high, and the railroad wouldn't want to delay that shipment. But in contrast, automotive, because the car companies usually maintain quite a constant delivery schedule, so they wouldn't value the time as much. And in that case, because of the higher holding cost for intermodal shipment, you can see on the top graph here, the orange dotted line, the delay cost is much more significant. And because of that, you see the red solid line, that's the total cost. When it goes to the minimum at around 4 batteries per locomotive, which is quite a high number, which means we have to put 4 batteries in a train if there's only 1 locomotive. This is in contrast to the automotive freight, where the total cost goes to minimum between 2 and 3, and the delay cost is at a much less significant portion. And therefore, just by the difference in holding cost, we can see why some commodity groups, such as intermodal, which are more time sensitive, would benefit from adding more batteries to the locomotives. Now we look into another example that is between the coal freight between Wyoming and Chicago. And now we put it in comparison with the automotive freight we just looked into. And the main difference is the range. So coal freight train actually has a longer range because coal freight is actually more energy efficient than other commodities, as you can pack more coal in a rail car. And the shape is also more energy efficient in terms of aerodynamics as well. As you can see here, 1.3, that means the coal freight car is actually much heavier than the automotive freight car. And because of this, you can see from the graph on the bottom right corner here, the total cost actually goes to the minimum at 1 battery per locomotive. So that means it's not sensible to couple a lot of battery tender cars with the freight, if the coal freight in this situation. And it's also because the delay cost is minimal, as seen here. And to assess this kind of insights in the whole American freight market, we've conducted a network-wide freight market analysis with all the US Class 1 railroad freight data in 2019 from the color wave samples. We aggregated the data into 22,501 markets of different origin destination pairs, different railroads, and different commodities. So the results shown here are actually the median of the optimal tender car arrangement with the minimum total cost. So in the graph on the left here, you can see intermodal is on the leftmost, and the optimal number of batteries is 4 for the median case. This is in contrast to motor vehicles, there's automotives, which is around 2, and coal is 1. So this agrees with what we have been discussing. Intermodal is a more time-sensitive shipment, so we want to put in more batteries per locomotives. But the same result actually may not go to the range. That is to say how long the train can run before stopping to recharge. And you can see actually coal has quite a long range. There is more than 300 miles, while intermodal has only like 250 miles, even if we pack in 4 batteries per locomotives in the median case. It's because coal is much more energy efficient and they don't have to stop as much, even with 1 battery. And to check whether our results would vary a lot with different range of parameters, we also conducted the sensitivity analysis. For example, this one with unit delay cost. So on the left-hand side is also the optimal number of batteries per locomotive with different delay cost factor. That is to say, we try to consider 50%, 75% to 200% of the unit delay cost. And then you can see for the intermodal, actually the result doesn't vary much because the delay cost is already around like 30% of the total cost when we put in 4 batteries per locomotives. But for coal and other heavier commodities, the optimal number does go from 1 to 2. And similar analysis on the charging speed, because this is one of the parameters with the greatest uncertainty in future technologies. For example, we have been considering 3 megawatt-hour chargers, 3 megawatt chargers, but I think the current scenario, usually the prevalent one is around 400 kilowatts. And we also looked into a case where there is a battery swapping. That is to say the railroads have pre-charged some battery tender cars, and when the train comes, they will just swap the battery with the train. Then the train can continue with their journey without stopping to wait for charging their batteries. And you can see here, when we use phase load chargers, we need a lot of batteries to obtain the minimum total cost. But when we go to like battery swapping, for most of the cases, we just need 1 battery per locomotive because the delay is actually minimal. So to conclude, we have developed an EOQ model to optimize the number of energy storage tender cars for different freight markets in the US. We considered the holding cost for shipment delay, as well as fixed cost for locomotive, battery, and charging. We arrived at a tractable solution with a convex total cost function. We also demonstrated the model with future battery electric technology parameters with 3 numerical examples of line haul rail freight and a network-wide freight market analysis of the US Class 1 railroads. So this can apply to the decision-making processes of railroads and rail OEM manufacturers for determining their investments in locomotives, tender cars, and charging infrastructure, both in terms of quantity and time horizon. That is to say, when to invest and how many locomotives they will plan to produce. So for the industry, actually, the insights to them would be these 3 points. The first one, we saw heterogeneity in optimal tender car configurations in different kind of commodities. The first one, like intermodal, which is lighter yet more time sensitive, that would favor more battery tender cars coupled per locomotives. While for heavier commodities such as coal freight with lower value of time, maybe just a single battery would be sufficient. The second point, we have demonstrated that with the current technological parameter assumptions, coupling multiple battery tender cars are sensible in many commodity markets across US railroads. So the railroads and OEM may really have to investigate into the strategies and operation requirements into multiple battery tender cars per locomotive. And the last one, from the sensitivity analysis, you can see even if the delay cost fluctuate like from 50% to 200%, the implication may be insignificant. But if the charging speed is slower, then we would need a lot more batteries to reduce the delay cost. In the meantime, when there is battery swapping possible, actually maybe single battery would be sufficient in many cases. So thank you very much for your attention. And if you're interested in more about rail decarbonization, as I mentioned, do go to newfriend.transportation.northwestern.edu to check more about our locomotive project. And I'm happy to answer any question now. Thank you.
Thank you, Max. Very good. I'm a bit too familiar with this research to be the one asking questions. So maybe if there are questions before anything that I have to say from anybody, please feel free to speak up.
I'll ask you a question, Max. So you had described the differences in terms of substituting payload cars for tender cars, and you compared intermodal versus basically shipping coal. And so this was somewhat counterintuitive, and I'm not sure why. So I expected the coal to be much denser and heavier, and therefore basically to require I was I guess there the relationship is that you need only 1.3, so you need only 1.3 tender cars instead of a payload car. Okay, that's due to the weight, right?
Yeah, exactly.
Compared to 10 when you have a basically
for the automotive case.
Yeah, I see. So then it is intuitive in terms of substituting. I think that so how many? I guess I'm not sure. So I guess where this threw me off is I'm not sure that you described how many locomotives do you have in one train versus the other. I'm curious, because even when you consider the number of tender cars per locomotive, these were also similar.
Yeah, actually in the analysis, we followed the existing train configuration. That is to say that how many train cars a locomotive is carrying, both for automotive and coal cases. And of course, they will be different. And in particular, for these two cases, usually automotive freight will still be traveling a lot faster than the coal freight. Because as you mentioned, coal freight is a lot heavier, and it is extremely time insensitive when compared to intermodal or automotive.
And but ultimately, I think it leads to similar ranges. Perhaps even the range of the coal trains might even be longer.
Yes, exactly. Yeah.
I see. Yeah. Nice work. Excellent presentation. I think that this was really nice, Max. Thank you.
Thank you very much.
I had a question if there are any others. So very great presentation. And so I wanted to I guess it's kind of like a comment and to see if you had any comments on it. When you mentioned that basically like slow chargers will require a lot more batteries per locomotive than battery swapping. I guess a railroad operator might be concerned, well, how many batteries or what fleet size of batteries would I need if I were doing battery swapping to have at my terminals kind of like sitting to have ready, right? To swap into train cars, because obviously they're going to need some redundancy at different terminals. So I wonder if there's I'm not asking you what the answer is right now, but I wonder if there's a way for us to find out like what that sweet spot of at what point is battery swapping better than just doing it, charging, in terms of the fleet size itself. I don't know if you have any comments.
Yeah, great question. And I'm sure you are a better expert in the network optimization than me. But I think that's actually involves both of the questions we are looking here. The first one is really the optimal payload for the line haul pairs. That is to say, between LA and Chicago, just to minimize the total cost for that shipment, then we want to pack in some batteries, for example, like 2 batteries per locomotive running on that line haul pair. And with battery swapping, there may be 1 or 2 in that case. And then you are also thinking about like how many batteries do we want to pre-charge in the charging stops? And then like how many batteries should be there waiting for the trains to come and to get recharged. So that would be more from a network perspective. Like especially we talk about like fluctuations, variability of the train traffic going on. So yeah, I would expect we need a network model in that case, instead of this simplified line haul model. Although the results from this line haul model can inform the bigger network model, how many batteries should the train be carrying? So that would probably be an output to the grander network model that I think you will develop this year.
Great, thank you.
Yeah, thank you. Great question.
Very interesting. Okay, so great, thank you. Okay, so with that, I'd like to introduce our second speaker. So Meredith Raymer is a third-year PhD candidate at Northwestern University, advised by Professor Hani Mahmasani. Her research interests are in multimodal urban networks and bridging gaps between urban planning and transportation engineering fields. So with that, I'll hand it over to Meredith.
Thank you. Okay. Yeah, I just couldn't find the button once I started sharing my screen. Okay, thank you. So today I will be presenting an area-wide network fundamental diagram for bicycles. So the motivation for this work is in the inconsistencies in bicycle networks. So these are some pictures as an example. There's disconnections as well in these networks, but this first picture is an image of what's called a sharrow. And so in this kind of bicycle infrastructure, the cyclist has the right to be in this entire lane. In the middle, you see a regular bike lane, and on the right-hand side, you can see this buffered bike lane where we have an additional buffer between the cyclists and the fixed traffic. So in each of these, and there could also be physical separation in these like second 2 scenarios as well. But in these, you can see this inconsistency in the amount of area that a bicyclist is able to travel, especially when you think about the width of a bicycle. They're nimble, they can move around a lot even within these lanes. So we also see in cyclists that when we have those different spaces, the number of cyclists that can fit in one of those lanes varies over time. So this is an experiment that was done on a circular track where they included a varying width. They put some bottlenecks in and we're testing these relationships. But the thing that you can see clearly from this image is that sometimes cyclists ride side by side. Sometimes that means that another cyclist can fit in between 2 cyclists riding side by side. And the staggered relationship makes it hard to organize or to identify lanes in a consistent manner so that you can measure your flow and density and specifically measure density in bikes per lane meter or per lane kilometer. So in pedestrians, when we have these similar relationships in self-organizing lanes and moving around an area, we measure density in terms of persons per square meter, per square kilometer. And so this work is aiming to extend that work of pedestrian network fundamental diagrams to cyclists. This hasn't been done in the literature on a network level. There's been some single bike lane links that have defined density in terms of area, but when they scale up to network level, and particularly when we have started, these authors have started to look at the car and bike interactions through network level fundamental diagrams, this density measurement for cyclists has not been used. So to do this, we used a simulation software called Sumo. There's limited real world data on cyclist traffic flows. There's also limited volumes of cyclist traffic flows. I think some of the best examples and work we've seen has been on bike lanes in China where they're reaching those flows. There's some, in the Netherlands, but getting real world data where we can see the full shape of flow breakdown occurring in the fundamental diagram is very hard to do. So we use the traffic simulation Sumo, and it was a 6x6 grid network. Another thing we wanted to test is when we're measuring over the area, what kinds of networks and network characteristics does that area matter the most for, and where is it important that we capture the area rather than just using the link-based measurement. So we tested a homogeneous network with varying widths, and in these, all of the links have the same width. We tested 1 meter, 2 meters, 3 meters, and 4 meters. Then we also tested heterogeneous networks. So here there's a random selection of links that have different distribution of width. So some of them are 1 meter wide, some of them are 4 meter wide, and that's all randomly selected. We also tested a heterogeneous network with non-randomly selected corridors. So the idea of if a city were to invest in a corridor for biking or a subgrid of bicyclists, that's what that network would represent. Did I miss a slide? Okay. Sorry. The demand for the networks is distributed evenly across the time intervals and randomly across origin and destination links. And the same demand is used in all networks. So even though some networks are double the area of other ones, we use the same demand, which is a little bit of a limitation. They use the fastest path routing based on the time of departure. And in terms of the car following model, the intelligent driver model is used, and that was validated for cyclists, but I do think that there's some limitations in using a car following model for cyclists, and that they might not always follow that behavior. So here's 2 examples of the network. This is a homogeneous network. On the left and on the right, you see a heterogeneous network. So those randomly distributed links. That might not be fully realistic for a real city, but just kind of to test and understand, are we capturing different relationships by measuring with area when the network is mixed? In terms of defining the variables, we used the derivations for ED's definitions. This is for the vehicle-based measurement. So this is comparing using density measured in bikes per meter. And so here you have your origin and destination links with the 3D space taken up by time to measure the flow and density. And then when we look at measuring by area, we're cutting this plane where you can see all of the X and Y components of the movement. So these are the formulas for those definitions. So you have the flow and the density, which are measured by the total distance traveled by all of the vehicles in the network during the time period derived, and the total time traveled by all of the vehicles network for that time period as well, which is the delta T in each of these. The key difference is L over in the top is the length of the network, and A is the total area of the network. So really that denominator is what's changing in both of these measurements. So looking into the results, this is on the left-hand side, you have the homogeneous networks, and on the right-hand side, you have the heterogeneous networks with the different areas. So this light pink color is the 1 meter wide homogeneous network. And you can see that we reach flow breakdown very quickly. Here we're measuring density in bikes per meter. And that's really the only difference we see in the shapes of all of these curves. The homogeneous network behavior looks pretty similar, even though this blue network is a 4 meter wide homogeneous network, and in green, it's only 2 meters wide. The shape looks pretty similar, and that's because we're using that same denominator. The length of the network hasn't changed. In the heterogeneous networks, we see similar behavior. It doesn't seem to matter what size the network is. These variables are mostly the same, or these shapes are mostly the same because we're using the length as the denominator. When we start using the area, though, we see a lot more differences in what's actually happening in the networks. So here, the density is measured in bikes per meter squared. And you can see how that makes the differentiation between how the shape of the fundamental diagram looks for each network. We see a little bit less differentiation in the heterogeneous networks. And that's because in each of those areas where we have the different widths, bottlenecks are forming as we go from the wider widths to the smaller widths. These are also a narrower spread of areas measured, but all of the bottlenecks forming is slowing down the heterogeneous networks. Interestingly, though, and importantly, on the heterogeneous networks, this pink color is that route-based heterogeneous network. And you can see that it's performing at a higher level than other similarly sized heterogeneous networks. So in these, the flow is also divided by per meter, so it's bikes per meters per second, which is because of dividing by the area and to get our bikes in per meter squared. But in the homogeneous network, since all the widths are the same, we can multiply that flow to get the normal or standard definition of flow, which would be bikes per second. And here you can see that at the same levels of flow, which makes sense, the larger networks are showing lower densities and reaching a little bit higher flow levels without as much density. So then when we compare across networks, you can see this light pink is the 1 meter wide. So that is our basically a single file biking scenario. But this again, you can see in pink that we're seeing higher performance from the corridors. And when we are putting in corridors with that higher performance, we're getting closer to what a homogeneous network looks like, where we're not experiencing those bottlenecks because we have consistent corridors of the same width. We're seeing higher performance from that. Some limitations of this are the simulation and simulated behavior for cyclists. And here I put, the way that Sumo does this is that bikes are going to be either small cars or big pedestrians. Even though the intelligent driver model is validated for cyclists, it's not, I think that the car following behavior doesn't fully represent how cyclists behave. I think one of the things about some cyclist behaviors, there's a social aspect to it. People go on bike rides together, and then they're not going to be following each other on some of these widths, like you would ride next to someone. And the simulation just considers a car following behavior. I also think that some of the leisurely aspects of biking, or what I know in walkability, they call it non-utilitarian walking, non-utilitarian biking, isn't captured by a car or bike following model. We think that not enough demand was seen in the larger networks, and suboptimal control contributed to some of the flow breakdown we saw in those larger networks. And this work, kind of, as I said from the beginning, is exploratory and definitional. So other work has gone ahead and used the density measurement as bike per meters to understand car and bike interactions. But we kind of needed to go back to the basics here and how we define density so that we can extend it to those car and bike relationships, especially when we think about separation. And with rule following behavior, are people abiding by that separation? Would a cyclist, even with a buffer, encroach on the car area because they can? So that's an important thing to look at. With that separation and also just general heterogeneity in behavior. So when the professional cyclists are out riding versus your casual cyclist, and then even with the adoption of e-bikes, how is that wider speed distribution and more adoption going to contribute to these flow and density relationships? To conclude, the 3D approach is used to define the pedestrian network macroscopic fundamental diagram is indeed applicable to bicyclists. There's clear differences that we can see depending on the area and depending on the network as well, that show us that it's important to measure things in this way. Of the results and of those features tested, heterogeneous networks have less consistent behavior than homogeneous networks, even with equal area. When we're adding width, we are improving the network conditions, and creating those consistent routes pulls us further to a homogeneous network with improved network conditions. Thank you, and I'm happy to take any questions.
Thank you. Super interesting, super great talk, Meredith. Any questions from the audience? I have a question. So yeah. So I guess like thinking about, well, I guess I have to disagree with a statement that you made of when you showed the heterogeneous network at the very like towards the beginning. You said this might not be so similar to what like city bike networks look like.
Yeah,
I think a lot of city bike networks probably look like this.
Yeah.
In the sense of, you know, maybe even worse than this, that there's like discontinuity, right? They just there's a bike lane, and then somewhere, I mean, I don't have to tell you, I think you know this,
Yeah.
and then they throw you onto a share or
Exactly.
worse.
Yeah.
So I guess like if we look at this, what I think like your research has a lot of insights for cities if they wanted to say like, how can I like what area or what corridor should I really be looking to improve, maybe like improve the width of, or actually construct a bike lane if I wanted to like capture a certain amount of flow. I don't know if you have any comments on like how you might adapt your research to answer like that kind of question.
Yeah, I think another thing that's a little bit missing in this network is like the disappearance of a bike lane. So like this is a fully connected. I think there's disconnections that should be tested as well. But I think one of the questions that I've been coming back to a lot is, would you rather have a sharo on a very quiet street like an Evanston neighborhood street? Or would you rather have a bike lane on a busier street, because you're actually, with the quieter street, you're getting more area for cyclists versus the safety and like need for separation? And I don't have an answer to that, but that's one of the things that I would really like to investigate is like what actually should be the policy initiatives, or like, even if it's slowing down, is it better to make a separated bike lane, or is it better to reduce the speed limit on that street for cars? And I think in terms of like the people who are activists for this, so the push is always for separation and for dedicated bike lanes, but that in essence is also limiting the space for bikes. And those are kind of things that I want to like wrestle with and balance out the conversation, because I don't just want 1 meter for a bike, you know?
Yeah, definitely. Okay, thank you.
I have a couple of questions. I really liked it. Thank you, Meredith, for this nice talk. And so as far as I understand it, like kind of a major, like kind of a switch in terms of the way we think about density is here. You're thinking about it, a number of bikes per unit area, where normally when people talk about cars, it's basically essentially per unit length, if I remember correctly. So I thought that was cool. I don't know if people have considered these types of things in synergistic behavior. And so what I mean by that specifically is with motorcycles, it seems to be somewhat related, although, and I think that motorcycles are widely used as commute vehicles in other cities, like much more so than in the US. And so I don't know that people are building dedicated lanes for motorcycles though. And so it's a little tricky, but I don't know if there are synergies there. And then the other question that I have, which is cool, is I don't know if there's any possibility of doing some empirical validation. And so in the US, I think that basically bike traffic is far too small. But I mean, you mentioned some of the places that come to mind, like the Netherlands. I wonder if there's any way of doing it.
Yeah, I would hope so. I mean, I've looked at kind of, there's a couple of Chinese studies, but they still, even with like showing their fundamental diagrams, they still weren't getting to a congested level to get that peak of it. And the pictures that they said of like, oh, this is our area of analysis, it looked very like there should be a flow breakdown happening, but still kind of the more compressible nature of cyclists and being able to get close to each other seemed to make it a little bit more stable, and not, even though from looking at a picture it looked very tight. But yeah, I'd hope to have some empirical research as well. I'm trying to I don't know how empirical it will be, but I'm trying to get Strava data.
I wonder maybe if cameras, if like kind of some cameras that they have in certain cities, they might allow for this. I very, very cool, like kind of really a nice connection to one of these alternative modes, and just really nice extension in terms of thinking about things a little bit differently. Yeah. Thank you, Meredith.
Thank you.
Any other questions for Meredith? Okay, so I guess with that, I'd like to thank both of our speakers, Max and Meredith, today for their great presentations, and stay tuned for the next session of VISIM, which should be happening in about 4 weeks in a month. So thanks again. Okay.
Thank you.